Okay, no questions? We move on. I'm going to pretend this is in two pieces. Shh. The indefinite integral. All we're going to talk about is antiderivatives and a new notation for them. Okay, I'm probably going to keep saying this until you get sick of it. The fundamental theorem gave us a strong connection between antiderivatives and definite integrals. In particular, part 2, which we've seen already today, tells you that if you want to find a definite integral over an interval and the function is continuous on that closed interval, then all we need is an antiderivative. If we can find one in a usable form, we evaluate it at the endpoint, subtract, and we're done. Okay? So again, we've got a close relationship between definite integrals and antiderivatives. Now we've discussed a lot of nice notation for differentiation, but we haven't discussed anything for anti-differentiation, which is why some of the stuff I've written has been clunky. So let's see if we can have some nice notation for the antiderivative. Okay? And the fundamental theorem, that guy in particular, suggests nice notation. And there it is. The indefinite integral, the last thing we talked about was the definite integral. The indefinite integral of a function is just the general antiderivative. Nothing new here, just notation. So if big F is any particular antiderivative of little f, we write the indefinite integral of little f is big F plus an arbitrary constant. And now we call that arbitrary constant the constant of integration. Okay, again, this is thanks to the fundamental theorem of calculus that we can come up with notation like that for something that we didn't have notation for before. Okay. All right, so if I write something like this, I'm saying give me the general antiderivative of x squared with respect to x. What is that? I've asked this before. X cubed over 3. Okay, x cubed over 3 plus c to get the general. Okay, nothing new at all here. We've talked about general antiderivatives before. This is exactly the same stuff, except we've got new notation now, and we've got a new name for it. And again, it was painful before to try to talk about this without the nice notation. Okay, so I'd have to write long sentences with lots of symbols. This puppy here is still called the integral sign. The function we're talking about is still called the integrand. This c is still that same old arbitrary additive constant that we talked about when we wanted to describe the whole family of antiderivatives, except now we have a nice name for it, the constant of integration. Okay. You plug in anything here, and you'll get a valid antiderivative. Okay, 1 pi minus root 43, whatever. Okay, any constant will give you a valid antiderivative, and so this describes the whole family of antiderivatives. And don't forget, if you ever want to check something like this, all you do is you differentiate this side, and you better get the integrand. Okay, you can check an antiderivative by differentiating. Questions about this thing? Yes. A few more seconds if you're copying. Okay, here we go. Definite and indefinite integrals, despite the fact they both have that lovely curvy thing, are very different things. Okay? You don't have to write all of this down. You could, or you could just look it up later. If you really want to write something down, write what's in this box. Okay, the definite integral, the one on the left, is the one that has these limits of integration specified. Given values of the upper and lower limits, okay, and given a particular function, what are we calculating? Essentially, we're calculating the signed area on that interval between the function's graph and the horizontal axis. Okay? And again, as I've said, that spits out a number. So if you're given values for a and b, and you know what your integrand is, you get a number, okay, out of the definite integral. The indefinite integral is completely different. Okay, the indefinite integral, you can tell what it is because there's no limits of integration specified. We define that as the general antiderivative. Okay? It's not a number. It's a family of functions, like that thing there. Okay? So what we're looking for here is the general antiderivative of the integrand, and what we get is an infinitely large family of functions, functions of the variable of integration, and they're parametrized, indexed, whatever, by the constant of integration c. Okay? So again, this guy spits out a number, this guy spits out a family of functions. Okay? And in that family of functions, I better see a c or something like it. And in this case, the variable of integration does turn up. Before, remember, it was a dummy, it doesn't turn up. Yes, sir?
What was parameterized?
Indexed, identified, something like that. So if I want to identify a particular solution in here, okay, how do I put this? So c equals 1 gives me one antiderivative, c equals 3 gives me another one, something like that. So it's the thing that sort of IDs them, something like that. It's their student ID number or something like that. Is that fair? Don't worry about the word. Parametric equations, if you've seen them, same kind of thing. Okay. Is that fair? Okay. All right, so let me just write some of that again here. Okay, let's look at this guy. General antiderivative. Okay, a family of functions are described. The variable of integration does appear. Unless the thing you were integrating was 0. And don't forget C. Okay, reading this out again. Saying this is the general antiderivative. It describes a family of functions. The variable of integration, this x guy, is no longer a dummy. It does appear over here. And don't forget this C. That's what gives you a general antiderivative. Okay? Number, family of functions. Very different things. Okay, remember when we talked about the definite integral? I said you could think of this dx as sort of an infinitesimally small width or change. Here you might go, what's the point? Okay, this might look a bit stupid to keep having that there. It matters what you integrate with respect to. It matters what you anti-differentiate with respect to. Just like, you remember when we did derivatives, it matters what you differentiate with respect to. Okay? We said dy over dx is different from dy over something else. So that matters, okay? You may remember chain rule, it mattered, and we'll see next class why it matters now. And that's it. Okay? So for now, in the indefinite integral, that dx just tells us what we're integrating with respect to. Which would be a bigger problem if we had more than one variable in there. Okay? We're good? Okay. The connection between these two types of integral is entirely due to the fundamental theorem. You don't have to write this. Okay, just appreciate it. Okay. Hey, guess what I'm going to say again? We've got a continuous function on a closed interval. We want the definite integral. What do? We evaluate an antiderivative at the endpoints and subtract. That's what this is, right? That's what the fundamental theorem part 2 told us. Okay? And that's it phrased in terms of the indefinite integral. Okay? The indefinite integral is the general antiderivative. We take the general antiderivative, evaluate at the endpoints, and subtract. We get the definite integral. Okay? The point of this is to show you the connection between the two types of integral and to show you that this notation makes sense. Okay? It makes sense. Look at how beautiful this is. Okay? That's why we picked this notation for the general antiderivative. Okay? And again, you'd never really write that when you're solving a problem, okay? You'd solve problems looking like this, okay? You would never write that. I just want to show you that so you can appreciate the notation and why it works. and why we came up with it. And for the record, over there we use an antiderivative, any one word. Here we have the general one. You don't have to use the general one. The C cancels out anyway. Questions? All right, I'm going to trip eventually. All right, we've already got some experience finding antiderivatives. You all okay here? I'm going to go on now. Okay, we've already got some experience finding antiderivatives. And we've already seen that when we're anti-differentiating, we can pull out constants and break up sums and differences, which is a nice thing, and we're seeing it a lot. You've seen this before, you don't need to rewrite this. Okay? Again, when we're anti-differentiating, we can pull out constants and we can break up sums and differences. And look at things piece by piece. Okay? Now that we have this new notation, we can write that a bit less awkwardly. We can write it like that. Okay, if we have a constant, i.e. something that has nothing to do with the variable integration, we can just pull it out of the integral like so. We have a sum or a difference. Okay, so you can make that plus minus if you like. If you have a sum or a difference, you can break it up into two integrals. Okay, again, we have a linear operator. We see a lot of linear things. Remember, log isn't one of them, just for the record. Okay, again, you pull out constants, you can break up sums and differences. Next. Consider not writing this down here. Do look at it, do know it. These are bits and pieces you're going to encounter often when you're finding antiderivatives or integrating. And we've seen virtually all of these recently, okay? I'm not sure if we've seen this one very recently, but you can totally get that one, and everything else we've seen very, very recently, okay? We were using all of these when we were anti-differentiating. All we didn't do was we didn't call this an indefinite integral, and we didn't have the curvy thing. That's it, okay? Apart from that, we were doing this before. Okay. Remember, anti-differentiation rules and definite integration rules are just differentiation rules in reverse. Okay? So all I'm saying here is that the derivative of this guy is this guy, the derivative of this guy is this guy, and so on. Okay? That's all this is. Okay? So if you're ever looking for an antiderivative, what do you ask yourself? You ask yourself, what gives me this derivative? So you want this guy's antiderivative, you say, what gives me that as a derivative? Okay? And don't forget to add the arbitrary constant, because you're looking for a family of antiderivatives. Okay? Yeah, nothing new here. You've seen all of this before. The only thing I will add is, in case this looks weird to you, this is just 1 over x times dx. Okay? You'll see it written like that a lot. Questions about this? Again, nothing new at all, just notation. Okay, a couple of units ago, I think, we learned a lot of rules for differentiating things. Okay, so given any respectable looking function, we can find its derivative. Okay, anti-differentiation isn't quite so nice. Okay, isn't quite so easy. There's no clear perfect recipe, and as I said before, sometimes you can't even find an antiderivative written in a nice elementary way. Know these kinds of things. Know that you can break up sums and differences. Know that you can pull out constants. Be able to think backwards. So if you see something, you can maybe sort of piece together what has that, what function has that derivative. There are also tricks for certain patterns. Okay, so basically, if you, we're going to talk next class about using the chain rule in reverse. Okay, and that's going to give us another set of things that we can anti-differentiate. If you take 128, you'll talk about doing the product rule in reverse. And that gives you another set of things you can anti-differentiate. Okay? But again, there is no general perfect recipe. Again, some things you can't even find the antiderivative in a nice way. So this is more complicated, more creative, more exciting than differentiation. Okay. Okay, example. Again, nothing new. Determine. The indefinite integral of, let's call it something else, 5y cubed minus 3 over y, I'll write it like that, fuse, plus 2 times 3 to the y, with respect to y. Okay, indefinite integral, you don't see any limits. Okay, so we're looking for a general antiderivative. Okay, if you want, you can do this. You can break this thing up. You can break up sums and differences. You can pull out constants. So if it makes you feel good to do that, go for it. Okay? If you want. All right, piece by piece. Divide and conquer. What is an antiderivative of this with respect to y? Go ahead.
1 over 4 y.
Thank you. Cool. Good, so that's all you do, right? 1 over 4 y to the 4. Good. Okay. You can always check, take the derivative of this, you should get this back. Okay. Participate team, what's an antiderivative of this thing? Ln, excellent, good. Okay. And because I'm a good person, I write ln absolute value. Okay, I wrote that to confuse. Don't be trying to use the power rule. Okay, it doesn't work there. Okay, this is 1 over y. Antiderivative is ln y, or ln absolute y. Okay. Yes. Okay, this guy? That's it. Okay, good. Okay, and you can think of that by working backwards. We did an example like that, or you can just write those things down or memorize them or whatever. Whatever works. Okay, it's just 1 over ln 3, 3 to the y. All right, what have I forgotten? C, very good. Okay. Again, it's a general antiderivative, so the variable turns up again. This is a family of functions. What else do I want to say? Oh yeah. Each of these guys has a sort of constant of integration associated with it. Okay. But what I've sort of done is I've lumped them all into this guy. That's cool. Okay. So it's sort of at a plus C1, a plus C2, and a plus C3, and I just sort of add those all together and call them all C. Okay. If you like, you can jump right from here to here if you're comfortable doing that, when you're comfortable. Okay? All right. Okay. Okay, guess what? Determine indefinite integral from 1 to 2 of the same thing. Okay, is this guy continuous on this interval? Yes, good. If we give you something that's not, we're mean, okay? Good, this guy is indeed continuous on that interval. Okay, what do? Write out a Riemann sum and find that no. We use this guy. Okay, we use the fundamental theorem. We use an antiderivative, evaluated the endpoint, subtract, and that's it. Life's good. Okay? Again, don't get these guys confused. They're asking different questions. Okay. Find an antiderivative. Ta-da. Evaluate the endpoints and subtract. 5/4 y to the 4 minus 3 ln absolute y. We're going to be dealing only with positive values of y, so you could drop the absolute if you wanted to. Plus 2 times, what am I doing? Plus 2 over ln 3. 3 to the y. 2, 1. Evaluate at 2, subtract, evaluate at 1. Good? Again, any antiderivative works. If you want, you could keep the c in there. That would be kind of pointless. It would cancel out in the subtraction. You could put pi root 423 in there if you want, okay? But it's pointless. It'll cancel out in the subtraction. Any antiderivatives, so just pick the simplest one, which is this stuff. Okay? All right. All right, I'll spell it out. So what do we got? 5/4. 2 to the 4 minus 3 ln, absolute 2, so just 2, plus 2 over ln 3 times 3 to the 2. Minus 5/4 1 to the 4 minus 3 ln 1 plus 2 over ln 3 to the 1. Okay? Presumably if you get really fluent, really confident, justifiably confident, then you can probably skip some of this, okay? You could probably go from this to the answer, but for now, don't. No mistakes, huh? Okay. All right, evaluate this thing. What's nice is that this guy's going to be 0, so that plops out. The rest of it we have to do, and we get the answer. 75 over 4 minus 3 ln 2 plus 12 over ln 3.
Do we have to find an exact answer, or can we just use it?
Depends on what the front sheet of the exam says.
Also, we can
In math, we like exact answers, right? But if it says you can approximate, then you can approximate. Yeah? Try it out. If you get something different, let me know. That's not self-doubt, that's for me. Okay? Yeah, in math you usually want an exact answer, right? And exact answers are nice. But if you're stuck, you do it to some number of decimal places. And if the exam lets you, you can do it to some number of decimal places. Okay? All right, any questions about this? We're good? And we move on. Function, family of functions, number. General antiderivative, signed area.